Okay, so the first speaker of today is Andrea Lodi from Cornell Tech, and he will talk about structured pruning of neural networks for constraint learning. So thank you very much, Andrea.
Thank you, Bartolomeo, and thanks everyone to be on time at the first talk, so always nice. And yes, so it's my pleasure and honor to actually kick off the workshop. I think it's a great idea to actually put people from different backgrounds together, as usual. So as usual is a good idea. Then let's try to get it right and communicate to each other. So this is joint work with my former student Matteo Cacciola, that is now since last week jumped to industry, and my colleague from University of Pisa, Antonio Frangioni. So what I will talk about today is, of course, in the realm of the interaction between machine learning and one of the topics that Bartolomeo was talking about before. In particular, I'm a discrete optimizer, so I've been doing combinatorial optimization and in particular integer programming for a long while. And then this is my, of course, my standpoint is to see how to integrate machine learning in particular into combinatorial optimization. Now, fortunately, I'm the first speaker, so I will, the fact of saying that the machine learning impressive success on, especially with deep learning, in beating human capabilities in the last years in terms of image recognition, language processing, and sequential games, for example, has led to the natural question to ask if we could apply machine learning in other contexts and in other scientific disciplines. And this is has been the starting point of a long journey at this point already, like roughly 10 years. In particular, the part I'm interested about this journey is the use of discrete, machine learning in discrete optimization. So this is a schematic overview. The slide is a courtesy of my friend and colleague Neil York Smith about essentially the interaction or the cross-fertilization or whatever you want to call it between machine learning and discrete optimization or combinatorial optimization in the slide. So there are several parts here in which, I mean, as you start here and you're thinking about combinatorial optimization augmented ML, so how to use the other way around, how to use combinatorial optimization inside some framework, machine learning framework, which is obviously, I mean, many problems in machine learning can be cast as discrete optimization problems, so this is a classical idea over there. Combinatorialization, model acquisition by machine learning, and plenty of other things. So the area in which, so there are two surveys which have been recent but not too recent about the use of machine learning for combinatorial optimization by myself, Joshua, and one of our students, Joshua Benjo, one of our students, Tom Provost, and more recently, more or less at the same time actually, a nice survey about what is called end-to-end learning that I will introduce in a second. Indeed, the easiest thing you can think of if you are a hardcore machine learning person is that maybe you don't need the combinatorial optimization, right? I mean, the problems are there. You want to solve the traveling salesman, and you don't really need complicated mathematical methods for doing this. You can just try to learn the solution, and this is the idea behind the end-to-end learning, in which indeed, given the problem definition, you are training a machine in order to actually spit you out directly the solutions of the combinatorial optimization problem that you like. For example, this has been tested already for almost 10 years for the classical traveling salesman, in which, of course, this is the traveling salesman has been let's say the sandbox for combinatorial optimization for decades, and became immediately popular in this particular area for using machine learning for combinatorial optimization. So this has been going on for a while. I have to admit that I don't think it's the most profitable way to go. I'm more into intricate type of interactions that one of which I will talk in the rest of my in the core of my talk. But this, admittedly, this has put the idea of solving combinatorial optimization, or at least the field of combinatorial optimization in the map for machine learning, and now in major conferences that there are a lot of sessions related to this, talks and so on and so forth, which definitely have been useful. And in particular, one thing that has been useful is to develop some new architectures that have been including graph neural networks. The use of graph neural networks in combinatorial optimization has led to actually pushing the bar in several contexts. The area I've been mostly working instead is this one that I call ML augmented combinatorial optimization, in which essentially you try to use machine learning for speeding up everything that is associated with solving a discrete optimization problem, and in particular, if you want to use it, if you want to use as a tool mixed integer programming, so a mixed integer programming solver. So in that case, your choice algorithm of choice is definitely generally branch and cut, and branch and cut is based on this idea of strengthening the LP relaxation by cutting planes, so making the LP relaxation tighter. And once you are thinking that there is not much more to gain in that direction, splitting the problem into sub-problems and solving those sub-problems by using the LP relaxation as a tool. So now, there are plenty of places in which this process is inherently let's say, heuristic, in the sense that plenty of places in which what you have is not precisely, let's say, strong or sophisticated mathematical tools for doing this, and the clear idea that emerged in the last 10 years is, well, maybe we, instead of developing, let's say, heuristics which are very tailored to the problem, maybe the idea would be to use data and so statistical learning methods in order to devise better heuristics which are faster and in general are data-driven, in order to look into these kind of things. And this has been leading to nice advances in the area of selecting variable for branching, in selecting this strengthening of the LP relaxation by cutting planes, in learning heuristics for primal heuristics for the problem itself, and one important major part has been also looking at into how to configure the branch and cut framework in order to be effective for particular classes of instances. So it's a nice, nice, I'm co-author, but I feel it's a nice way of putting this 10 years together in this paper with my colleagues and friends from university, from TU Delft, so Karen Ardal and Neil York-Smith, and their student Lara Scavuzzo. So this is going to be the topic, the main topic of my talk, keynote talk at ISMP. The two parts that are two fundamental building blocks that have been explored in this direction indeed are what we call learning properties. So in the idea of learning properties, instead of just, as before, replacing completely combinatorial optimization, the idea is to say, well, maybe machine learning could be useful for, orienting the way in which the discrete optimization MIP, OR, so whatever you want to call it, algorithm is going to run afterwards. And this is learning properties or learning to configure in the previous slide. And indeed, the idea is in this scheme to have a machine learning algorithm that is actually helping to make an initial decision related to the problem problem, and then run your favorite solver after that. So the interesting thing is that this has been already somehow into production. So for those of you which are familiar with mixed integer linear programming and mixed integer linear optimization in general, there are very powerful solvers, among them the sponsor of this conference, one of the sponsors of the conference, Gurobi, so we hear a talk about later on, not about the solver, but in general from people from Gurobi, from Robert from Gurobi. And the idea is those software tools are very powerful and very mature, and they actually routinely solving a bunch of different applications in discrete optimization, which are actually formulated in the industrial context. So now, making sure to be able to developing scientific results that are actually are incorporated into the solvers is a significant, let's say, is a significant milestone for realizing that what a certain area of discrete optimization is becoming routinely mature to actually be used in the practical context. And in this particular area, so learning properties or learning to configure, there are already examples of algorithms which have been developed in industry, in academia, and then have been incorporated as tools into the solvers. For example, this is linearization configuration tool in which for a mixed integer quadratic optimization problem, Cplex, another one of the big solvers, is deciding using a machine learning algorithm to if linearizing the quadratic part of the objective function or not linearizing it. Again, this is an example of a decision that we don't understand fully from the mathematical standpoint, and by essentially using data, we get a nice approximation of building a nice heuristic for doing this, and this is what currently is already in default version in the solvers. So this is one of the examples. I think the first one, I think Gurobi has other things of this type. Skip, the open source solver, has other examples, and Express as well. So a little bit more complicated, you get into the point of saying, well, I don't want to make one single decision at the very beginning of the process, but I would like to make an iterative, I would like to make one decision type that is repeatedly done within the solver made by machine learning. And this is actually the scheme that you can think of in this case. Every time the OR algorithm gets into a state in which there is a decision to be made, then the machine learning model is actually called in order to make the decision and going back to the framework. This is actually the classical approach for variable selection. So variable selection, in the few words I used for giving you the let's say, for explaining what branch and cut is about, saying I'm splitting the problem into subproblems, and the way in which I'm doing is actually picking a variable and fixing it to, if it is a binary variable, supposed to be binary, is actually fractionally in the linear programming relaxation, is actually either I fix it to 0 or I fix it to 1. And deciding which one of the variables I want to start to branch on, so I want to start to split the problem with, is actually a difficult task. We don't understand it mathematically, and using machine learning for doing this has been already somehow advanced in terms of quality of the solution, of the results. It's not in production, coming back to the point I was doing before, for several technical reasons that we can, that would be a little bit longer to explain, including the relationship between CPU and GPUs, because those decisions are actually made in the best possible way if you're running machine if you're running neural networks, models on neural networks, based on neural networks, and this is actually effective on GPU, which is not effective on the CPU. So let me finish this long introduction with one single more slide, which is about an area that has been gaining a lot of attention recently, which is called, in the previous slide was called decision focused, here it's called decision aware learning. This is about more connected to stochastic optimization and the idea of using machine learning to predict part of the solution or the problem, but actually making this into a loop with an optimization method that is supposed to give you feedback on the quality of your prediction. So the classical one classical problem, one very well-known problem about using machine learning for optimization is that the objective function, so the loss function of machine learning is generally about accuracy, so how accurate you are in predicting something, but this is not necessarily aligning with the quality of the prediction at the end in terms of in the pipeline what you want to use the prediction for, which is actually optimization. And without a profitable loop on this, it would be actually sometimes very hard to use the prediction within an optimization framework. So today, what I will try to talk about is somehow a kind of intricate interplay between machine learning and discrete optimization, in which I will show you how to essentially use machine learning for designing your optimization problem, but at the same time how to use combinatorial optimization in order to actually make the overall model, let's say, behaving better in a MIP context. And this is, for a more general situation, is about making the neural network small. So again, this is based on this joint work with Matteo and Antonio, and which is on the archive, is under revision in Operation Research Letters, and the idea behind the scene is what has been already explored by several authors, which is called the constrained learning, which is in the title of my presentation, finally. Thanks for waiting until the end. The idea is not only using machine learning for, or not necessarily in this case using machine learning for deciding so for making some decisions on my discrete optimization problem, but here actually is using machine learning to formulate my combinatorial optimization or discrete optimization problem. So this has been explored by several authors over time. So there's I think the first reference is what is called empirical decision model learning by Lombardi and Milano. And then there is actually software called Janos by Bergman's group at the University of Connecticut, and the group of Dimitris Bersimas and Dick Den Hertog in the Netherlands has been doing a lot of work in this direction. So what is constrained learning about? So let's take an example. So let's assume that we want to allocate scholarships for the 100 students that Meta was talking about here at Princeton, and allocate scholarship to admitted students. And one idea is to understand if, let's say, what is the correlation between the probability of the student to enroll and the offer itself, is to look at some data about the students, for example, GPA, SAT, received scholarship offers, maybe from others universities, and so on and so forth. And then one can think about training a machine learning model to approximate this correlation, right? I mean, you're using a function G that is as an input the GPA, the SAT, the offer, and whatever else type of features that you want to use, and is able to do an approximation, or so essentially computing some prediction on the quality of on the probability that the student is going to accept the offer. Okay, very standard. The problem is that the offer itself is a decision, right? I mean, it's not a data at this point. So you can use it, you can treat it as data because you have historical offers that you have given to previous students. So you have historical data to train this model. But from the technical standpoint, when we actually get into the point of deciding those offers, this is actually data. Okay? Sorry, this is actually a variable in the problem. So you are to decide about what is going to be the data of your prediction model. So then the point is one would like to have this model included inside the optimization framework that has to allocate the entire budget in order to make offers to the students. Okay? That's the basic idea. So the point is, sometimes it's hard to write as a linear programming model or as a linear programming plus integer variable some specific characteristic of the problem that you want to solve. And in particular here, I'm claiming that in this toy example that, I mean, writing down the correlation between this data GPA, SAT, and offer in order to produce this probability, it's not going to be easy if you want to do it by linear programming. At the same time, this is going to be very useful inside your optimization framework in order to decide the offer themselves. So, fortunately, I mean, you can be tempted of saying, well, I want to use a neural network for doing this, so for producing this. So G is going to be a neural network model and producing this probability. And so the point is, well, how can I put these two pieces together? So I know I have a tool, good tool for powerful tool to produce this probability, and at the same time, I would like to embed this probability inside an optimization model. Fortunately, the observation made a few years ago by Matteo Fischetti and Jason Zhou, and actually built on top of this observation by many others, the good news is that once you have trained the neural network to actually produce this function G, eventually the problem that is actually extremely difficult to solve, so training a neural network is a complicated process that requires, of course, a lot of data, a lot of computational resources, GPUs, and so on and so forth, becomes much easier if you are looking at it from a mixed integer optimization standpoint. Indeed, once the neural network is trained, and you recall that the training of a neural network means assigning weights to the connections between the neurons in the network, then the only thing that is actually, if you're using ReLUs, so rectifier linear units, then the only thing you have to decide is essentially how to activate or not activating the neuron itself, and which is based on this idea. So at any point L plus 1, what is happening is that the ReLU is deciding if passing the information, because WLOL, so the layer before plus the bias is actually greater than 0, or is actually, if it is not passing the information, if it is smaller than 0. Okay? So now, this is actually, each neuron can be written as very simply as a mixed integer linear optimization problem, in which this is actually the positive component and the negative component of the input, computed by the previous layer, and in which this activation or not of the neuron itself is based on just using a binary variable. Here is Z of L for neuron L, in which I'm saying, okay, if this is positive, I need to put ZL equal to 1. If it is actually, instead, if it is negative, then we simply have this situation in which the ZL equal to 0 will actually put this 0 and will activate the other one. So what I'm trying to say is, once if you think about the complete training of a neural network, This is actually, you can cast it as a gigantic mixed integer quadratic optimization problem, but actually multilinear, but you can always push it to a quadratic. So gigantic problem of this type, which is non-convex, so the relaxation is non-convex, and so it's a terrible problem to solve, and nobody would like to solve it as a mixed integer quadratic optimization problem. But once this training is done, once you are happy with your G function here, those W here become essentially data, and at this point the only thing that you have is a big mixed integer linear optimization problem in which the decision variables are the activation or not of a neuron based on the input that you are receiving it. Okay? So this is actually just a simple observation, but leads to actually a very impactful situation in which you say, okay, I'm collecting data, I'm training my neural network, but now, coming back to my example, the offer is an input, so I would like to take the neural network, which is already trained, and incorporating it, embedding it into my mixed integer linear program, because now it's another part of the mixed integer linear program, and it is a piece that can be easily incorporated into my framework. Okay? So now, how does it look like? This is my neural network, very simple, a feed-forward neural network with 3 inputs, 2 outputs, and 2 layers of 4 nodes each. And this is the way in which the metrics will look like. So the metrics, constraint metrics of my mixed integer linear program is just putting together the connection between the positive part of neuron 1, the negative part of neuron 1 with the input on this side. This is about the transition from one layer to another. This is actually the output. And if you want to look at that for a specific neuron, here the specific neuron that is on the second layer, this is activated by the input, the 4 inputs that are coming from the previous layer, and which are this positive and negative here. And this will be the input, the interaction, these 2, with the output on the other side. So it becomes a completely defined set of constraints, which are the ones that I've described here, set of constraints plus integer variables, binary variables in particular, that are doing the job for you. Okay? So now you have a powerful tool to, let's say, incorporating complex functions, which are that you can learn from data by machine learning models. By the way, this can be done also not with neural networks only. You can, of course, write in the same thing for logistic regression or other types of models. If you want to do a decision tree, for example, in decision tree case, there are, if you keep the size of the decision tree under control, you have mixed integer linear programming models in order to actually define an optimal decision tree, by the way. So now, what I'm saying is, I have a complex function that is actually hard to represent by mixed integer linear, but once I trained a neural network for doing this representation, and then I can take the representation and incorporating it into my favorite MIP model and try to solve it as it is. Actually, this is the way in which Gurobi has decided to go, and in the sense that based on these approaches in the literature, Janos I was talking about before, and the work at MIT and the Netherlands. So there have been enough evidence that this could be actually a good tool for mixed integer optimization, and so Gurobi has developed an open source Python interface to import a trained neural network inside a MIP. Okay? And somehow the idea is a good connection between these two worlds, so I can use machine learning for building a part of my model, and at that point I have actually an automatic tool for importing the neural network and using it in my favorite MIP solver. So Gurobi did quite some nice algorithmic work in order first to recognize the network. So because the input is given to Gurobi, but at that point the Gurobi the solver has to recognize that there is a neural network. It's not, it doesn't get it from directly as let's say as a flag in the model. And also some algorithmic tools in order to actually speed up the computation. But according to the communication, so one clear problem about this is that we tend to use over-parameterized neural networks that are actually very big, and then when you include them into a MIP model, makes the model gigantic, especially I mean, it's linear now, it's not quadratic anymore, so good news. But if you're using a very deep neural network with a lot of layers and a lot of neurons, the problem is that still you have a lot of binary variables. And I put it under the carpet. This component here is actually what we call a big M, right? I mean, this is actually an activation trick that we use in order to decide about let's say, the bounds, because we don't know the bounds of those variables. Tiago here in the audience has a beautiful survey about how to actually write good models for this, how to write, let's say, how to exploit the combinatorial structure and how to actually writing tight relaxation for this problem, but still, it's actually a complicated problem. Tiago, do you agree with me, right? So it's a complicated problem. So now then the point has been, okay, so what do we do with that? So it looks like a very powerful tool, but has scalability issues. Well, what came to mind is that, scalability issues are not coming for the first time in neural networks, right? I mean, the idea of training over-parameterized neural networks has been around for a long while, but there is in the context of using those predictions, neural networks, into what is called edge computing. So, for example, your cell phone or less powerful architectures, the problem is that this is becoming an issue, and it is a scalability issue in that context as well. So, model compression has been around for decades, and there is a vast literature on doing this for reducing the size of the network without actually losing too much accuracy. And somehow our work is actually putting these pieces together and says, well, maybe we can use pruning in order to do an intermediate layer, not neural network layer, but layer between training your neural network and using it as an input for constrained learning. One can reduce the size of this network by using pruning and model pruning. So network pruning. So very quickly about this, model compression, edge computing. I mean, in edge computing, there have been several ways of doing this compression, this quantization, knowledge distillation, many other ways, and one of those is called pruning. And the idea is simply to actually remove, in this particular context, which is called the structured pruning, what I really want is to remove some neurons, because I actually put to zero all the weights of the edges or the arcs that are actually entering in that particular node. So if I, in a graph representation node or in a neuron, neural network representation is a neuron, so if every one of those is equal to zero, so the weight is equal to zero, then of course I don't need, I mean, this is going to be, the linear combination is going to give me zero, and so I don't need the output either, and I can safely remove the node. And the neuron. So I want to do this without losing accuracy, and this is what Antonio and Matteo and I have been working on for a while. We have a paper in SciAm Journal of Mathematics for data science, I think. Yes, CMOS is called that. So, and one way of doing this is by regularization. So this is your training of the neural network classical, so in which you have the loss function, and besides the loss function, you're using a regularization term in order to make those I mean, the network sparse. And in particular, the classical regularization implies using L2 norm for the problem. And our proposal, and this is why I'm saying that there is a bit of an intricate interaction here, is that what we are been suggesting is to think about it as a discrete optimization problem and actually looking into this in a slightly different way. So the idea that we pushed in that paper is to do two steps. So instead of using a classical L2 normalization or L1 normalization, regularization, sorry, I'm using an L0 normalization to penalize the non-zero weights. So really L0 means I want to count how many of those are actually non-zero, and I want to minimize such number, okay? A weighted combination of such number. But of course, this is actually highly non-convex. It's not easy to deal with. And so what we are doing here is we are, first of all, doing what we call perspective, what we don't call it, but it's called perspective reformulation of the problem and taking the LP relaxation of this. We call it structured perspective regularization, and this is actually what is happening here. So I will not go too much into the details, but in blocks, what happens is that this is your regular loss function for the training of the network. Then you have somehow parameters here to actually let's say controlling the regularization. And here you have the L2 term for minimizing the weight of the arcs, plus the L0 term, which is actually here counting how many of those I need. So note here that the binary variable at zero term is saying, well, I have I and j here. J is the index for the specific neuron, but I is the index associated, sorry, the j is the index of one particular arc that is entering into as an input of this particular neuron. I is actually the index of the neuron itself. So which means that I'm allowed to actually kill the neuron only if all the weights of the arcs that are entering are equal to 0 at the same time. Okay? And so this is actually a model, a regularization that takes into account L2 and L0 at the same time, very hard to solve. And so the step here is to do what we call, what is called perspective reformulation. So you play with it by, it's relatively easy to show that this model in which you take the binary variable and you're using it as a denominator for the first term is actually just a reformulation of the problem as it is. And after that, based on this formulation, you can do the linear programming, the continuous relaxation of your problem. It's not linear programming anymore because there's a quadratic term, but you do the continuous relaxation of the problem. So you are getting rid of the requirement about the variables to be binary, and at that point, you get a stronger continuous relaxation for the problem that has been shown to be actually effective for doing the job. So putting all these pieces together, the idea is I'm training my neural network. I'm getting out a very nice, the accuracy I like to have in order to having a good approximation of my prediction, good quality of the prediction. At this point, instead of actually using directly Gurobi to input this neural network inside your framework, what you have to do is that you have to pass through your favorite pruning method. In our case, is the structured perspective regularization, produce a smaller neural network that you have to retrain. However, there is this catch, it has to be retrained, and then going inside your MIP. So now, does it work? Well, this is actually one of the examples that are the most, let's say, the most satisfying or interesting for this area of integrating the MIP, the trained neural network into a MIP. So this is called adversarial example search. You assume it to have a classifier, and the classifier is you wanna find, and you have a classifier and you have an example. This example is classified as, let's say, negative from your classifier. You would like to have the closest possible example, so input, closest to your negative classified example, such that it's classified in the other way around, so positive, okay? So this is useful in many contexts. For example, for robustness, for defining the robustness of a neural network, is also very useful for doing counterfactual analysis, and so on and so forth. So explainability, so explaining why the neural network is predicting in a way or another. And so you say, well, if you change a little bit your behavior, maybe you're going to get alone the next time, and stuff like this. So this is a nice application for constrained learning, because here is the model. So think about why now is the classical, let's say, output of the prediction of this is going to be our neural network. And you want to find delta here is the distance between the given original example and the new example that you are building, okay? And you want such a distance to be bounded, so small, and you want that the predicted is value, or in a binary context, the prediction is positive versus negative, or the predicted value is actually as different as possible. So bounded the distance, now the prediction is as distant as possible. And for binary means positive versus negative, otherwise it would be a different measure. So this is one problem in which that the people in machine learning, the community cares a lot. And in general, I think for explainability issues is very important in general. And so we tested the problem by using our strategy. And these are the results. So in the graph, in the table on the left, we are using like a small distance. It's delta equal to 5 here. And what you can see is that the effect of using this pruning in Gurobi. So here you can see that a small network with 2 layers and 50 nodes per layer. So has a very good accuracy and can be solved by Gurobi in roughly, 10, 15, 20 seconds. So by using the pruning, like of the network, what you get here is a pruned network with, in the first layer, only 39 neurons, and in the second layer only 43, which is a moderate reduction, but is a small network here. But the computing time becomes now in the order of seconds. Okay, so essentially you gain a factor of 10. So when you're getting a little bit bigger, the situation becomes even nicer. 2 by 100, going from, let's say, 40 seconds to 15, but actually when you get larger and larger, 2 to 200, Gurobi starts to get in trouble. In half an hour is not able to prove optimality of the problem, so gets into time limit, but instead we scale very well, and we stay at, or the order of, let's say, 10, 15, 20 seconds, 30 seconds at most. And when you go to even larger, so 6 layers and 100 neurons, and the situation gets very complicated in general for Gurobi standalone, while after doing this normalization, you get, regularization and pruning, you get a much stronger result. Here, for example, you get a very nice reduction. So now, the good news is that if you look at the column here, the accuracy you are having, you don't drop accuracy. So the model pruned in this way is actually very good. So we have additional results that I don't have in the slides. These are very recent, made by the revision. The question was, okay, so this is actually good news, but I mean, maybe this is a little bit overstating the situation because those neural networks are already giving a very nice accuracy in small. So why do you want to go much larger for getting more or less the same accuracy? Here you get 97 versus 97.55. So it's not really like a big difference. So we did some additional tests on instances in which the accuracy otherwise would have been bad, so you really need the large neural networks first, but actually this reduction is still doing good. So all this, in all these instances, the situation is that there is no at distance 5 example that is actually classified in the other way around. So by enlarging a little bit the distance, so how far away you want to go from your input example, then the problem starts to have a yes answer. And the interesting news is that in this particular case, on the larger networks, first of all, it's not obvious that we don't have a theoretical proof that we keep the same thing because we are changing the networks, right? I mean, so in theory, if there is a yes answer in the original network, now we're changing the classifier, so maybe not a yes answer in the new network. The answer, so far empirically, this is always the case, and the good news is that when Gurobi is not able to actually giving us a yes answer, so gets into time limit, doesn't have a feasible solution at that point, we can get a feasible solution and map it back in the original network is also a feasible solution. So this is actually giving us some, let's say, empirical evidence that the method is working from a computational standpoint and also has some, let's say, nice empirical properties with respect to the problem that you want to solve in this particular case. So I'm actually wrapping up. I overall feel that we start to have solid evidence that this integration between machine learning and combinatorial optimization is effective. So there are integration into the solvers. There is actually started to have this more intricate, let's say, examples of one helping in one direction and the other one helping in another direction and putting things together. I think it's a very nice area, and I'm very keen to actually excited to learn about many other directions in control and other areas in this today's. My favorite one is one of my favorite topics is the fact of try to use machine learning to actually repeatedly solve the same problem, which is what companies do all the time. They're not buying Gurobi to solve one day the TSP and the another day the facility location. Generally, they are solving the same problem over and over. So we should give them a tool for doing this in a much better way, and statistical learning looks like a good strategy for that. And thank you very much.